right, so here we go. So in the last video, we learned about how to calculate the center of mass of a system of particles, right? So you've got these little particles floating in space. You've got this little guy here, and this little guy here, and the center of mass is, oh, it's right here, right? Okay, and at the end of the video, we did that problem that had the car and the truck, right? And I did not say this in the video, and I wish I had. The reason we were able to treat the car and the truck as particles is because relative to the distances between them, the size of the car and the size of the truck were very small, okay? So that was a little bit of an oversimplification there, okay? But so then the question is, what if we wanted to find the center of mass of the car by itself, right? Or like a hammer or something like that, right? And once we do, what does that sort of buy us, okay? So on my page for this chapter, there's a link to a 1 minute long video from MIT, and it's just them throwing various shapes across the room. Once under regular light, and then the second time they're thrown again with the center of mass marked with orange, and then it's under a black light. And so what you can see is the center of mass follows a nice parabolic path, the same as what you would expect if you threw like a tennis ball, right? So even though when you throw a hammer, it kind of flips and rotates and turns all over the place in the air as it's going through the air, the center of mass still follows a very predictable path, okay? Which is what this whole slide here says. So cool. So we know that, if you throw this, this baseball bat here, the center of mass follows a nice predictable path. Great. How do you find the center of mass, right? So now instead of looking at particles, we're looking at this one rigid object, in this case a hammer or a baseball bat or whatever, and trying to find the center of mass for it. Okay, so basically all you're going to do is you just imagine each of the particles that make up that object, and you do the same thing we did before, right? This baseball bat here is made up of molecules, and each of those molecules can be treated as a particle. And so you just, go, well, the position of the center of mass is the mass of the first particle making up the baseball bat times its position, plus the mass of the second particle times its position, plus dot, 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 dot for 7 bazillion particles, divided by the combined mass of all the particles, right? And solve it, right? But that's not really practical, right? You're not going to do it that way. And if you ever do have to do it that way, it becomes a calculus problem, which we will get to later here in the video, okay? So, but before we get there, most of the problems, or a lot of the problems, are going to be about an object that has uniform density. So by uniform density, what I mean is that, suppose you've got a brick. So here's my brick. Okay, so the idea is if you chop this brick up into teeny little cubes of equal size, if it is of uniform density, what that means is each little chunk is going to have the same mass, okay? So any chunk of the same size will have the same mass as any other chunk of that same size, okay? And so when you've got a symmetrical object like this that has uniform density, the center of mass is exactly where you'd think it would be, which is it's supposed to go right through the center. It's at the geometric center of the object, okay? Cool. Now, sometimes a thing will be symmetric in some axes, but not in other, right? Think about a book. Let's see if I can explain this. So here's a book. If you look at a book from the side, it looks like this, right? You've got your binding, and then, the pages. Okay, and then it's, okay. So vertically, your center of mass is probably at the center, right? From top to bottom, it's probably at the center. But on this axis, the center of mass is probably a little bit over this way, right? Because the binding is heavier than this end of the book, okay? So how do you deal with that, I guess, right? If you didn't follow that example, I apologize. We'll get better examples here in a minute, all right? So imagine a thing like this. So we've got this, this shape here, all right? It's a metal plate. It's uniform, i.e. uniform density. And we're going to try to find the center of mass of this thing, okay? So to be clear, if you can't see, can't read the the screen here for some reason. This guy has a length of 6d. This guy has a length of 6d. And then this little block that we've got cut out in the middle is 2d by 2d. So 2d, 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 etc. Okay? So we're going to try to find the center of mass. So let's do vertical first. So I notice that this thing has some symmetry. If I draw a line across the x-axis, it's completely symmetric about that, right? So that means that the vertical position of my center of mass is just 0, right? Because there's exactly just as much mass above it as there is below, and in the same position, okay? So it's not just about mass, it's also about position, okay? But horizontally, that's not the case, right? So let's find our horizontal center of mass. So what I'm going to do is I'm going to break this thing up into chunks of equal mass, okay? So, no, not chunks of equal mass. I'm going to break it up into symmetrical chunks is what I was trying to say. Okay, so there's 3 chunks, right? And each of those chunks has a center of mass. Oh, hey, Mr. McGuire.
Hello.
Each of those chunks has a center of mass, right? So since each of these things is symmetrical, the center of mass is at the geometric center. So there's, call that number 1, call that number 2, and we'll call this number 3. Okay, so let's write out where the positions of each of those things are, right? So let's see. So for particles 1 and 2, remember this, I need a new color. This distance here is 3d, right? This little distance here is d, right? Because it's half of a 2d block, which means the distance from my origin is 2d. So the position for particle number 1 is 2d, and the position for particle number 2 is also 2d, right? What about the position for particle number 3? Well, that block is 4 by 6, right? And so horizontally, let's see, how do I want to explain this? So this guy here is 4 long, right? So that means it's 2 away from the edge. So that means that this little distance here must be -1. Cool. So horizontally, that's where the center of each of those 3 blocks are. All right. Now the next thing we got to worry about is mass, right? We got to worry about the mass. So because this thing is uniform, it turns out that the mass is proportional to the area. Twice the area is also going to mean twice the mass. All right. So let's do this. Let's define a new unit of mass. Let's let our unit of mass, let's let m represent the mass of a square with an area of d by d. Okay. Okay. In other words, an area of d squared is going to have a mass of m. Okay. So with that in mind, let's find the area of each of these blocks, and then we can replace that with our mass, right? So from this point forward, m represents the mass of a block with an area of d squared. Okay, so let's go back. Do this again. Let's break this up again. So let's see. So that guy is 2d by 2d, so that's 4d squared. Oops, try that again. 2d by 2d, so that's 4d squared. This guy is also 2d by 2d, so that's 4d squared. And this other chunk is 6d by 4d, which is 24d squared, right? Which means that the mass of particle number 1, 4d squared, so that's 4m. Mass of chunk number 2, 4d squared, that's also 4m. Mass of chunk number 3 is 24d squared, which is 24m, right? Okay, cool. So now we're just going to find our center of mass. So the position of our center of mass is x1 times m1. Well, I guess we usually do m times x, don't we? So m1 is 4m times x1 is 2d plus m2, 4m times x2 is 2d plus m3 is 24m times x3 is negative 1d. All divided by our total mass, which is 4 plus 24 is what, 32m? And so what do we get there? So you're going to get 8 plus 8 minus 24, so you get negative 16 md over 32m gives you negative 1/2 d. So that means that horizontally, my horizontal center of mass is at negative 1/2 d. So the center of mass is going to be right here, right? Where that's 1/2 d over. All right. Oof, it's a rough one. How are we doing? All right, not too bad. I think we got time to do our last one. Okay, so that is that. Break it up into chunks. Treat each chunk as having a mass proportional to its area and a location at its geometric center. So now, what if it is not uniform density? All right, so what I want you to do, and I've got this little graphic here down at the bottom, I want you to try to imagine a long, thin rod whose density changes along its length. All right, I've represented that here. Notice this end of the shading is really light. So that's like, you know, this end is maybe made of styrofoam, right? Something really light. And then maybe it's made of like a, you know, maybe like poster board, right? And then maybe like a really light wood, and then a heavy wood, and then, I don't know, aluminum, and then lead, and then gold, okay? So that as it goes along, the material is becoming more and more dense, okay? So it says, imagine a thin rod whose density changes along its length. So it's getting more and more dense as you go to the right, okay? So we can describe the linear density. We're going to use the Greek letter lambda to represent linear density. Okay, and it's mass per unit length, all right? Now notice it's changing, right? So for us, our linear, I like this lambda that I made here. So our linear density, according to the problem, is lambda equals 0.6x, where x is the number of meters from the end of the rod. So in other words, over here we're at x equals 0. Over here, x equals 2 meters, because it tells you that the rod is 2 meters long. Okay, so the idea is, if you break this rod up into little chunks, the chunks get successively heavier and heavier and heavier and heavier and heavier. Okay? All right, and so what we want to do is we want to find the center of mass of this thing. All right? So, a little bit of calculus, which is a drag, but the nice thing is every single one of these problems is solved exactly the same way. All right, so here's how you're going to do it. So, oops, that's not what I want to do. There we go. Okay, so here's what you're going to do. So, to find the position of the center of mass of a thing like this, you're going to take an integral. What you're going to do is you're going to integrate the position of the particle with respect to their mass, which is really weird. I still don't completely, like, this doesn't make a lot of intuitive sense to me, the fact that you're taking your integral with respect to mass instead of with respect to position, but that's how you got to do it. And so what you got to do is you got to integrate until you get to your total mass. You're going to integrate from a mass of 0 up to a mass of capital M, where capital M is the mass of the whole thing. All right, so I'm going to try to get better about making my m's differently. So this is a lowercase m, and this is a capital M, okay? So, and then you got to divide that by your total mass, okay? So in order to solve this, it's the same 4 steps. I think it's 4 steps. Yep, same 4 steps every single time you do it, okay? And once you learn the process, it is easier, okay? So the first thing is this. We don't want to integrate DM, okay? You have to change it, all right? So in order to do that, we have to do what's called variable substitution, or variable replacement, I guess. Replacement of variables. So here's what we're going to do. So remember, by definition, lambda is the mass per unit length, okay? So if you take a tiny little chunk of mass and divide it by the tiny little chunk of length, that's what lambda is, okay? And so it turns out you can rearrange this. If I multiply both sides by dx, you get that dm is lambda dx. Okay, so that's always step number 1. All right, so for us, dm is lambda dx. Okay, but remember, for this specific problem, lambda is 0.6x. Okay, so lambda dx becomes 0.6x dx. Okay, so that's what dm is. That's our first step. I guess I should have given that a credit. Find dx. All right, so that's step number 1. Step number 2. You got to find the mass of the rod. This is weird. I didn't give you the mass of the rod. I just told you it's 2 meters long, and I gave you this stupid linear density thing, right? So how do you find the mass? All right, so quick calculus tangent. All right, suppose I gave you this. Suppose I told you, so this is a side note. I would like you to figure out what is the integral between 0 and 7 dx. Okay? Okay, well that's really just the integral of 1 dx, right? So what's the integral of 1? Oh, well that's just x, right? Evaluated at 0 and 7, which is just 7 minus 0, which is 7, right? Oh, so it just gave me this upper bound, right? So by that same logic, I feel like then I ought to be able to integrate between 0 and capital M dm. Oh, and that would give me capital M, right? Because when you integrate dm, you're going to get m, little m, right? And then when you plug it in, you're going to get capital M. Oh, okay. Oh, so this is how you find m. All right, so let's see. So that becomes the integral between 0 and capital M of dm. But remember, we just found dm a minute ago, right? And dm was 0.6x dx, right? Oh, so what I actually want to do is, now I'm not integrating with respect to x, I'm not integrating with respect to m, I'm integrating with respect to x. So I don't care about the upper bound of the mass anymore. Now I care about the upper bound of the length. So I'm going to integrate between 0 and 2 meters. Oh, and we totally know how to do that, all right? This m is meters here. Oh my gosh, too many m's. All right, so what is the integral of 0.6x? Well, that's the same as 0.3 times x squared, evaluated at 0 and 2. So if you plug in 2 squared is 4 times 0.3, so you get 1.2 kilograms. So that's the mass of our rod. So that is always step number 2. And it's always the same thing. It's if you want to summarize this, it's basically just mass equals the integral from 0 to L, where L is your length, of lambda dx. Okay. The problem is this equation isn't on your equation sheet. You know, the equation sheet just gives you this guy, so you really got to kind of know how to solve it. All right. So solve for dm, and then swap your variables out. Okay. There's a problem exactly like this on your homework tonight, so you guys can try it. We'll go over it, and then there's another one on the next night, so you can try it again. Okay. All right. So that's step number 2. Step number 3 is we got to find the, so we just found the bottom part of the fraction, right? We found m. Now we got to find the top part of the fraction. So let's do that. So step 3. We need to now find the integral of x dm. Oh, well, that's the same as the integral of x. Remember, dm was just lambda dx, so that's 0.6x dx. We're integrating with respect to our position, so we got to get from 0 to 2 meters, right? Because that's how long the thing is. So that's the integral from 0 to 2. Let's see, x times 0.6x is 0.6x squared dx. So the integral of 0.6x squared is what? 0.2x cubed from 0 to 2. So 2 cubed is 8, times 0.2 is 1.6. And that is kilograms times meters. Kilograms is the mass, meters is the x. Okay, and then step 4 is solve it. Position of our center of mass is the integral of x dm over m. So we just found x dm, that's the 1.6 kilogram meters. The mass of the whole rod was 1.2 kilograms. Divide it out, and you get 1.3 meters. Okay? So, try it on the homework, and we will for sure go over it. Like I say, this is new calculus, I know, for a lot of you, and the process is exactly the same every time you do this, okay? And it's a thing you absolutely have to know how to do, because there are other things like this later on. When we get to rotational inertia, you'll have to follow a very similar process. So it's important you know how to do this, all right? There we go. How did we do this time? 22 minutes.